All right, here we are recording here. This is class number 9, packet 6. That's last week. So you should have turned in your 5B black and blue. That was due Friday. There's 3 ways to turn it in. Some of you dropped it on my box, my porch. I don't know whether you put it in your, maybe you put it in your folder. I don't know. I'll have to go through and check that, I guess. Probably the easiest way to do it was to submit through Canvas, which very few people did. This week, I handed out the second set of test 6A practice problems. Last night I had them available, and we're not doing QR codes. I had them available online for the PDF of it. The QR codes idea is okay, but it takes up space. And if you have a link, if you're doing it electronically, you have a link anyway. And so it's probably easier just to go to the YouTube channel, and for test 6A, there's practice problems. There's 21 total. I think 16 of them have a help video. I'll try and get some of the others done today. And if not, it'll be tomorrow. So that's today. Tomorrow we'll meet one of you maybe. Flex day, which doesn't really affect you guys, is Wednesday. Thursday, though, is the test for in-class students. Now, for you all, it's Friday, and the PDF of it will be emailed to you by 2 p.m. Friday afternoon. You'll have until Saturday at 6 p.m. to either submit it or turn it into the porch. Okay. Prefer to turn it to the porch so I can mark it up. You know, it saves me from having to print it off. But if not, it looks like the prom is this weekend. And so is May. That's good. Okay, next couple of weeks, a lot of AP testing. As far as tests in here in physics, there's really nothing except on the 12th of May, we start our blue day for test 6A, okay, the blue points. There's not really black normally on these tests, just blue. And that'll be due the 14th of May, and then we're down to the last couple of weeks. So it's getting there, folks. Only 4 more Mondays, not counting this one. All right, what else we got? Last time on Friday, I showed you this video, and that got me a copyright problem. But they only said that you can show it as long as you don't make any money off it. Well, I'm not making any money off this. But then we did the AC/DC. Everything else is fine. Everybody's cool about it, about the Flashback Friday. And I played like maybe 5 seconds of that AC/DC song. And that shut down the whole video. Because the Gene sent me, he wants some money, right? So that, if you were looking for this weekend, it was in copyright holding. Finally, last night, after trimming some stuff off, I got it back on. So it is there. Tree Fest is this Friday, April 30th. This is Alexi Muslik will be there. There's him and his dog, but he will be there and working with you guys. And I'll give you more details on this later on this week. I think it starts at noon Friday. We didn't do any stargazing today because there wasn't any homework assigned over the weekend, nothing official. Did our joke Monday. Okay, so let's start off talking about this. I found this, there's actually an animation on this, but I can't find that animation. There's an animation where it shows, this is all computer graphic, but it's actually wind tunnel data on I think it's 737 with the wheels down. Now, when you're landing, as somebody pointed out today, well, then you kind of want drag, but you want a certain kind of drag. When you're taking off, though, you don't want any drag. You definitely don't want drag then. So the drag around a wheel assembly before it comes up is very important. This green, this is all the turbidity currents. That's all the wake zone that occurs around all the landing assembly. So if you can design a better shape or a better paint, or better material, or shark skin, or make it like a golf ball, put dimples in it, something that reduces that wake zone. If you can reduce the wake zone down, you can drop off drag and the plane will take off easier, and it'll save fuelage. So that's an example of aerodynamics engineer, aeronautical engineer that would be working on that kind of stuff. Okay, well, the first thing we're going to do is work on this. I sent them to the board. This is for 6.2. I sent them to the board to work on 10A. So I will pause it here in a second and I'll give you a chance to do 10A and then we'll talk about it. So I'm going to hit pause. There's 8 of you here. All right, we're back on the air here. And that's so far, all I've done is I've shown that the force of thrust up and mg down. I was telling them that air drag is not really a factor. It is always a factor, but you say, well, it's negligible with these big forces here. Okay, so once you have that established, next thing you do is you do your summation of forces in the y equals MAY. And the force up is force, normally you say up's positive, force of thrust, normally, sometimes you don't, but in this case we do. Direction of motion is positive, right? Force of thrust minus mg equals MAY. Okay, so I'm trying to solve for force of thrust, so let's isolate that variable. And there are a couple of these, kind of like this one, where if you take A and B together on the practice problems. So that's mg plus MAY. All right, so now it's that's your isolated variable equation. You always want to box that in, circle that, draw my attention to that. And then, so you get your partial credit. Or I can see where you made your mistake. Force of thrust equals then mg, they told us, I should have put that down there, it's 981 newtons. That's the mass, or the weight, sorry. So it's 981 newtons. Plus, well, for M, now I got to pull the G out of that. So that's 981 newtons divided by, I got to divide out the G. Well, that's convenient, 9.81 meters per second squared times 3 meters per second squared. Okay, ta-da, that's the numbers. Now we go ahead and solve for it. Force of thrust then is 1281, because that works out to be nicely 10 kilograms. 1281 newtons. Okay, questions on that? That's the warm-up drill. Now let's go to B. B is if the gas is escaping out the nozzle at a speed of 350 meters a second, how fast is the rocket losing mass? So somebody tell me, what kind of velocity is this?
Escape velocity.
Right. So there's different kinds of velocity. There's V naught, initial velocity. There's V final, final velocity. There's V bar, average velocity. And now we have another one, V sub E, escape velocity. So this is escape velocity coming out the back of, so if I have a rocket here, it's got a little nozzle. Coming out the back, this gas is coming out with a speed of 350 meters per second. That's relative to the rocket. So the force of thrust then is m dot VE. Now that's not actually the equation for force of thrust. Here we go. This is the true rocket thrust summary. This is from NASA, from the Glenn Research Center. And this is all the stuff that you need to go into making the true thrust equation. So mass flow rate, This is something you learn if you go into aerospace. Exit Mach, exit temperature, exit pressure, exit velocity, all that stuff. So you end up, though, a lot of this cancels and you end up with that equation. That's the true thrust equation. We don't include this because most of it can be gotten here. 90% of it usually comes from there. So we just go with that first part. And a lot of people do. We just go with the first part of the thrust equation, m dot VE. All right, so here we are, m dot VE. So we're solving for m dot. M dot then is force of thrust divided by escape velocity. So we have 1,281 newtons divided by 350 meters per second. And that gives us what, 3.66, 3.67, something like that. Newtons over meters per second. What? What is that? Newtons over meters per second. That's a silly unit. Anybody have a comment on that?
Don't you have to make newtons like kilograms times meters per second?
Yeah, so when you get goofy units like that, and sometimes you'll leave it in these weird, like impulses, Newton dot seconds, you leave it in newtons. But here, this is not, that's kind of a nonsensical. So you're right. So we take that, we open up the suitcase. If you open that up, you get kilogram dot meter per second squared. And then we're dividing that by meters. That's the same thing as multiplying by the reciprocal. So multiply by seconds over meters, bring out the green kill pin, seconds, meters. I'm left with kilograms per second. So that's what that really just becomes, kilograms per second. The rate that something's coming out the back. Okay, so we got 3.67 kilograms per second. So that's about losing about 8 pounds, 8 pounds of fuel coming out the back per second. That's a lot. 5 seconds by 40 pounds came out the back, and that's pushing this rocket. It's about a 10 kilogram rocket. 100 kilogram rocket, pretty good size rocket, 220 pounds, about the size of a person. All right, so 11 and 12, I'm going to leave that for homework for you. We're going to go on and do some other stuff, but 11 and 12 will be your homework for tonight. This is the last time I give homework this week. Of course, there's always the practice problems, but I want you to concentrate, knock these two out, but I want you to concentrate on the practice problems tonight, tomorrow, and Wednesday night. The big test on Thursday. Okay, now what? Let's see what else we got. Okay, so most of the rest of the hour, the time we have, the next 30 minutes, we're going to talk about buoyancy. At least we'll get going on it. May not go all the way to, we'll go about 150 or so. Oh man. The thing is, I come home and I eat. I don't eat breakfast, so I eat breakfast when I get home. I rush down, wolf down cereal and a bunch of fruits and yogurts and stuff. And they're good, they're carbs, but they make you sleepy. I got to stop doing that. Eat me a good old steak or something. Anyway, so here it is. This is the main thing you got to know for buoyancy, is that any partial, it's an object that's either floating in water, sinking in water, or floating around in the air, you're going to have more force on the bottom than you do on the top. And the reason is this thing called overburden. All that, like when we're walking around, if I'm walking around in just in the street, all this air above me, there's a column of air that goes up 500 miles. And it gets thinner the further up it goes. So I'm walking down to the thickest part of the soup, and that's 14.7 pounds per square inch, right? That's what's on me. But the bottom of my body has more pressure than the top of my body. And that basically the difference of the force is buoyancy. So this is buoyancy here. I'll give you a chance to write that down. And I'll put screenshots up. But so it's this overburden that causes the buoyancy. People don't believe it, but like if a helium balloon will let it go, it's because that takes off quickly, but it's because even if there's no wind, there's more air pressure at the bottom of the helium balloon than the top of the helium balloon. Fluids are weird. It happens in solids too. There's overburden for gas pockets and underneath the earth. If you're a mile deep, you got all this rock on top of you. That's a lot of pressure. Okay, so buoyancy is this difference in pressure. Pressure is simply force per unit area. So you take that out. It's the difference in force. That's what buoyancy is. That's why it's always straight up. Here's the formula for it. It's fairly simple. It's the rho, that's the density of the fluid, not the pressure. That's a rho, RHO. It's a symbol for density. And so it's density of the fluid displaced, the volume of the displaced fluid, and then times G. So unit wise, I have it here as well, just to show you that it does work out. It's always a good idea. It's something called dimensional analysis, just to look at it and say, do these units work for this formula? And they do. You end up with units of kilogram meter per second square, which is newtons. Okay. So that's the buoyant force. Now let's talk about it a little more. So if I'm in Colorado, and this is actually taken in Colorado, this picture, it looks like Colorado, maybe it's Hawaii, because I'm starting to think it's Hawaii now, because that looks like Mount, what is it? We've been up there before. My family is way above the clouds. It's the observatories in Hawaii. So here he is. Let's see that's where we're at. 14,000 feet. This person, man or woman, I don't know who it is, finished off the water bottle. That's empty now. It's full of air. Open it up, let the air in. Okay, capped it. So there it is at 14,000 feet elevation. He drops down to 11,000 feet. I'm sorry, 9,000 feet. And so at 9,000 feet, now look at it. Look what happened. And then this at the end is at 1,000 feet, right? Yeah, 1,000 feet, about where Norman's elevation is. So there's no crushing, just that's just air itself. Air crushed that plastic bottle, the air pressure. So at the opposite effect, if you fill something full of air in Oklahoma and took it to the top of the, mountain in Pikes Peak, let's say, it should explode. Now it doesn't for water, because water doesn't expand as much as air. It does a little bit, but so a bottle of water, because someone asked that in class, well, why don't my bottled waters all blow up when I go up? Because water doesn't have the expansion coefficient of air. It's not so pressure dependent. So this brought up in class a discussion on how is it changing as we rise above sea level. So this shows the potential or the altitude above sea level, and these are in meters. So we start with, and this is something that I try and put on an equation sheet, but it's a lot of numbers. Anyway, we start at sea level, then we go to 1,000 feet, about where Oklahoma is, and you can see this has the temperatures. Let's look at one column at a time, okay? So let's just block everything else out. All right, so just look at, first off, the temperatures. So we rise up, this is, 1 kilometer, 2 kilometers, 3 kilometers, about 10 kilometers, look at about 8 miles or so. No, less than that. Anyway, so looking at kilometers, how high above the earth you are, look what happens to temperatures. it's dropped. This is Celsius. So Victor's from Germany. He said, yeah, about 18, 19 degrees Celsius is comfortable. So at 0, we're at 15 degrees Celsius, but look what happens. It quickly drops off. And that makes sense because there's less air, above us. So it's dropping off. But then look what weird happens. It goes down as you expect. And then all of a sudden it turns around and it comes back up. The temperature rises. Why is that? Look at that. It goes all the way to almost comfortable. Well, not comfortable and not too bad. It's about 28 degrees Fahrenheit, negative 2.5 Celsius. That's at 50 kilometers above the Earth. So what is this temperature inversion? All of a sudden it gets warm? Well, in the Earth, we walk around the troposphere. Troposphere is where all the weather occurs. It goes up to about 10 miles. About 10 miles up. Above the troposphere, there is the way up there, 10 miles up. Look out your window. What's up there? 10 miles up, it goes to the stratosphere. And that is lower pressure. So at 10 miles up, you're at what? About 15 kilometers. So you're getting down in temperature there. But at 10 miles up, you go to the stratosphere and pressure is really starting to drop off now. Like you'll have these anvil-shaped clouds that come into Oklahoma. They like supercells, right? And when they get up to a certain height, they all just spread out like an anvil. They're called anvil shape. And that's because they're up there in the stratosphere where there's less pressure and it can spread out. You get above the stratosphere, you get to the mesosphere. And then finally around in here where this temperature kept going up, it's something called the thermosphere. Okay, when you have radiant energy up there that gets blocked back up, that speeds up air molecules enough where the temperature is still too thin to really breathe, but the temperature is not so bad up there. They're moving at pretty high speeds to give you that feeling of about 28 degrees Fahrenheit. Then it cools off again. So then you go to the exosphere, and the exosphere then kind of trails off. Our atmosphere is about 500 miles thick. But when you get out to like 300 on, it's starting to just get really thinned out into what's called the exosphere. Okay, so that's temperature. Let's see what else we got. G, notice that G doesn't hardly change much at all. If I just look at these two columns, height versus G. All right, so I'm blow this up. So for height versus G, that goes actually 1,000 below, but when you get to Oklahoma, you're about 9.80, 9.81. Then you get above like 7,000, 8,000 or 8 kilometers. You're in the range of big jets flying up there, and they still experience 9.72. So they still experience almost the same. We're at 9.81 or 9.78. When you even when you get up there to 80 kilometers above the Earth, you're still at 9.5. Now, space shuttle and stuff, the ISS is like 200 kilometers above the Earth, but it's still like 9.4, 9.3. It's pretty much the same gravity like we'd experience here. And the question is, why do they float? And we answered that a while back because they're in free fall. They're falling back to Earth. Okay, so that's G. Look at another one. Mm-hmm. 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 Come on, man. Stupid. Okay. Get rid of that. Open this up. Pressure. Let's do a pressure and density because they're both related. So the density of air, right where I'm standing, where I'm sitting here, this is 1.2 kilograms per cubic meter. But look how quickly it drops off. You get up to 15 kilometers, you're at 0.19. You're less than 10% of the density at 15 kilometers. You get up here, you get up to 80 kilometers, the density is practically nothing. So yeah, there's an exosphere, but look at the density. This is kilograms per cubic meter, whereas 1.2 in this room right now versus 0.000018. I mean, 10,000 times less dense up there. Absolute pressure is related to it. That's simply force per unit area. So of being hit by particles. So there's just not enough particles to hit you up there. All right, so that's a good table. I think I'll put this on an equation sheet. All right, let's see what else we got. We're just kind of doing some odds and ends today. Oh, okay. So back to buoyancy. If I'm on a hot air balloon, I'm trying to rise. I got to heat that air up inside it to make it can expand. And then it's the same amount of air, but expanded, therefore it's less density. Therefore it gets pushed up because of the buoyant force of air. If I am sitting at 100 degrees Celsius, if my temperature inside is 100 degrees Celsius, that's pretty hot. That's boiling water. I will rise because I have enough difference in pressure, enough difference in density that I'm going to have that overall buoyancy beats mg. Here, if I'm just trying to stay neutral flight, I'll make it about 95 Celsius, and this depends on the pressure in the area. And then if I want to descend on about 90, I cool it down to 90, quote, cool air, that's going to condense the balloon back enough to make the density high enough where now it starts to sink, okay, slowly. Okay. Yeah, let's talk about the iceberg. Hold on. Okay, so on the iceberg situation, you've heard that 90% of it's always tip of the iceberg, right? 90% of the iceberg's beneath the water. And the reason for that is something called Archimedes Principle, which basically states, there's a whole thing here on it, and I'll put that in the screenshots. But basically it states that that the amount of water, the weight of the water displaced by the object, by the submerged object, or by the object that's floating, is equivalent to or equal to the weight of the object. So if I put even floats, I put a 10-pound piece of wood in water, and most wood would float, right? It will displace 10 pounds worth of water, and it'll still be above the surface, right? A battleship that weighs tons, let's say a battleship weighs 50 tons, it has to displace 50 tons of water to float. And it does that by ballast tanks, right? Steel that a ship is made of is about 7 grams per mil, so about 7 times the density of water. But you put mostly empty space, air, in a ship, and that brings the overall density less than 1. For an iceberg, thank goodness, ice expands. It's one of the few elements that expands, or molecules that expands when it goes from a liquid to a solid. If it didn't, all aquatic life would die every time it froze. I don't think we'd have life on Earth if it didn't do this. But it's about that hydrogen bonding and the structure that it takes. And so ice is about 10% less dense. So that's why on an iceberg, you'll see about 10% of the iceberg above the surface. The rest of it's all below. And it's because it displaced an equal amount of water, but because ice expands, that little extra in the expansion is what's floating on top, if that makes any sense. But that has to do with buoyancy, right? I mean, the water's holding up the iceberg. Okay, so you can tell we were down in Panama. My brother-in-law has a place or has land down there. So we went down to Panama to hang out by the beach for a while. And then you can look at big, huge ships coming in, right? And then through Panama Canal and all. So you can see these ships when they come in. You can know if they're empty, if they're full, because this is called drafting. And so you draft here, and that's how much of the ship is underwater. That's the draft. And so, like this ship, I can tell that it's not drafting very deep. So this is probably empty, mostly empty of containers. Whereas this ship is full, and you can see how deep that draft is. So the deeper the draft, the heavier, the more the stuff's on board. So you can you'll see them. This, I don't know why I didn't put the picture in there, but this is marked up the side. It tells you how much drafting it is. Sailboats, they have these keels, different kinds of keels, but they're trying to, keep stability that way. Get this rid of that guy if I can. I'm buffering or something. What the heck? Okay, get rid of that. Oh, okay. It is grouped. Hold on. Ungroup. All right, now. Okay, so this is typical sailboats with their keels. So you want to, using Archimedes Principle, this also gives you stability. You got a lot of torque from the wind, so you have to be able to balance that. Then there's just something here on specific gravity. Let's move on though. Okay, we're about done. Oh, last thing. Okay, this is it. It's in the news right now. These Indonesians, these poor sailors that lost their lives. Horrible way to go. But they're at 3,000 feet depth. So the question is, how does a submarine rise and fall in the water? If a submarine is made of steel, which is 7 times the density of water, how can it possibly rise? I can see it sinking, but how does it rise? And the answer is these ballast tanks. So if you're in port, once you go out to the water, you're ready to dive. They open up these tubes down here, and the water comes in. Okay, so all the surrounding ocean water comes in, fills up to the level you want. That's going to sink you. Then your density now, overall density goes greater than 1. It goes 1.5, whatever, and you sink. So as the water fills up here, you're going to sink more and more. When you're down at, say, 300 feet below sea level, and you want to rise, then you got to push this air out. You got to open up these valves now, these compressed gas valves, and then let the air out it's got to blow at a very high pressure. These motors can be broken easily. So it's got to blow the water out here, and then that will reduce your density less than 1 overall, and you'll rise in the water. Well, what happened, and I don't know for sure, they just found out that it's not recovery. If you don't follow the news, like 65 sailors died because their submarine, this is happened this weekend, the submarine would not rise, and it went to the bottom of the ocean at 3,000 feet. There's nobody that can survive that. In fact, a submarine can't survive that. It's too much pressure, too much overburden at that depth. So what might have happened, I'm speculating here, is what might have happened is there could have been a blow. I mean, there could have been a torpedo that blew a hole in the side. But what also might have happened is this compressed air tanks failed to work. And if they have backup systems, but if all those fail, they can't blow the water out of their ballast tanks. They can't rise. That could have been the problem, but most likely there's some kind of explosion on board. And then I was watching it with my wife. She goes, "Oh, what a horrible way to drown." And I'm thinking, I don't want to say this to her, but I don't know if they drowned, because if you go, well, look, last story. But Bill Fix was a teacher, is my mentor teacher, and he was in Vietnam. He was in the Navy though, and so they were on a diesel. This is like 1961, 62. He was on a diesel sub, And when they were in port, they would take a cable and they would stretch it across, him and his buddies there, from bunk to bunk. You have bunks up here, you know. And so they would stretch that, then they would cinch it down tight. And so in port, the cable would be like this. But when they got to 300 or 400 feet depth in the water, you know what the cable looked like then? The cable would be bent like this. And they can tell by, and that's because the entire fuselage of that submarine squeezed. It's called bulk modulus. The whole thing squeezed because of all the surrounding water pressure. So that's a tremendous amount of pressure. They could tell how deep they were, by the way, by how much it sagged. They had it rigged up a little system where they could tell. But that just shows the kind of pressure that's on you. So at 3,000 feet, no submarine is meant to go to 3,000 feet. If it had a breach at that point and the water came in and the pressure equalized, the good thing about it is the sailors didn't have time to drown. They imploded. That pressure will just like that, basically like that bottle we looked at, because that's just too much pressure change. So it's a horrible, horrible thing. I can't imagine. I would never want to be on a submarine. And this talks about rising. The yellow is the compressed air. The blue is the water, how you rise and fall for a submarine. Okay, we'll leave it there. We'll talk about fish and sharks and stuff tomorrow, and then we're going to get on to other things. But buoyancy itself is pretty interesting. Okay. So that's the show for today. If you have a question, I'm going to post the rest of those. I'm going to post the rest of those problems today or tomorrow. I'll have them all posted by tomorrow by 7. Most of them are already posted already, but do check YouTube. It's under the playlist Test 6A practice problems. And if not there, then look on the Facebook group and guide number 3. You'll see the practice problems are underneath each one of those. Okay, Sophia already caught me on a mistake, and I fixed that. And Sophia, I owe you 5 Facebook points. That I don't know what I was doing there. It was stupid. Okay, so stick around for questions. Otherwise, I'll see you all tomorrow. Have a good Monday, everybody.
Mr. Ask, I have a question. Yeah. So out of all the questions on the practice problems for test 6, how many of those are going to be on the
about 8
test?
I haven't written the test yet, but I'm guessing about 8. I'll write the test. Probably not going to write the test until Wednesday, tell you the truth, but I imagine about 8 or so out of 21.
All right. Thank you.
You bet.